Alright, in this very quick video, we are going to go over the equations for capacitors in series and in parallel, because this is something I forgot to cover in my intro to capacitors video a few videos earlier in this playlist. So before we talk about that, we are going to quickly go over a reminder of how this works for resistors, which we covered much earlier in the playlist, and then kind of talk about the analogy to capacitors. So you may remember that if you combine a bunch of resistors in series, that is just the equivalent of one big resistor with equivalent resistor value equal to the sum of the resistances of all the individual resistors. And intuitively, that kind of makes sense because as you're putting more and more of these things in series, there's more resistance that the current has to flow through, so the total resistance goes up. Conversely, if you put a bunch of resistors in parallel, so add as many of these as you want, then the equivalent resistance, we say, adds inversely. So 1 over the equivalent resistance is 1 over R1 plus 1 over R2, and so on. And the net effect there is that as you add more resistors, the equivalent resistance actually goes down, which is something that students find a little counterintuitive at first sometimes. Like, wait a minute, hey, if I'm adding more resistors, how is the resistance going down? But you can think of it as kind of each time you add a branch here, you're giving more paths for the current to flow, so you are decreasing the overall resistance. And again, that's all covered in an earlier video in this playlist. Here we are pretty much going to do the same thing, except we are going to talk about capacitors in parallel first, because I think that one is actually the more intuitive one in this case. So if I add a bunch of capacitors in parallel, again, you can keep adding as many as you want in parallel, then the equivalent total capacitance is just the sum of all the individual capacitances, C1 plus C2 plus C3, and so on. Or if you want to write that in fancy summation notation, it could be the sum from I equals 1 to n of Cn, where n is your number of capacitors. And if you remember the equation for the capacitance of a single capacitor, C equals epsilon times A over D, where this is the, I always forget if it's permittivity or permeability, permittivity of the dielectric material, filling the gap in between the capacitor. A is the surface area, D is the distance between the plates. This one kind of intuitively makes sense because as you're adding more plates in parallel like this, it's like you're just increasing the area. That's kind of like just having one giant capacitor with surface area equivalent to the sums of all these individual capacitors, and since that term is in the numerator of this fraction, then as you increase the area, you increase the total capacitance. That makes sense, and there's your equation for the capacitance of capacitors in series. Capacitors in parallel. I'll write that down. Capacitors in parallel. Apologize if I've been saying series by accident. Now, for capacitors in series, this is the one that maybe is a little less intuitive at first. So as we add capacitors in series, we're going to get the same type of mathematical relationship we had for resistors in parallel. The capacitances are going to add inversely, so as you add more of them, the total capacitance goes down. And again, writing that in summation notation, 1 over the equivalent capacitance is equal to the sum of I equals 1 to n of 1 over Cn. And the way to think of that is that as you're adding more of these in series, you are adding up all of these gap distances, and that is in the denominator of this fraction. So as you add more and more capacitors in series, that gap actually gets bigger, and as a result, the total capacitance goes down. So now that you know how this works for both resistors and capacitors, it's important not to get them mixed up, okay? If you're just recalling these equations from memory and you are more used to working with resistors, then it's kind of easy to slip up and forget that it's switched for capacitors. So if resistors add in series, add inversely in parallel, capacitors add in parallel, and add inversely in series. And in practice, this is useful not just as a mathematical exercise that you have to do on your homework, but because just like with resistors, physical capacitors tend to come in certain common sizes. So for example, if you are designing an RC filter, something we have talked about the step response of in a previous video, we'll talk about the frequency response of this in a future video, and say you do some calculations and say, oh, you need a certain resistor value, but you don't happen to have that resistor in your kit, you already know that you can combine resistors in series or parallel to get that resistor value that you need. It's the same thing for capacitors. If you need a specific capacitor value, but you don't happen to have that capacitor value handy, you can combine capacitors in series, parallel, or a combination. So again, we went through this with resistors. You could put two capacitors in parallel and series with another capacitor, and so on, all to boil down to a single equivalent capacitance that you need. So again, we'll be talking about the frequency response of an RC filter in a future video, but for now you have your equations for capacitors in series and parallel.